So let's talk a little bit about change of variables now. With a formal change of variables, you completely rewrite the integral in terms of u and du or any other convenient variable. Like if the integral is already in terms of u, like if they just pick the variable u, then you can use v or something like that. Although this procedure can involve more written steps than the pattern recognition method illustrated in the first example, it's useful for integrals that become more complicated. The change of variable technique, it uses the Leibniz notation for the differential. That is, if u equals g of x, then du equals g prime of x dx. Like du dx equals g prime, then multiply both sides by dx. And the integral in theorem 6.13 takes the form f of g of x times g prime dx takes the form f of u times du. Okay, so let's look at an example. Let's find the integral of the square root of 2x minus 1. Well, first, you have an inside here, so let u equal 2x minus 1. And then calculate the differential du. So if I take the derivative of that, it would just be du equals 2 dx. Okay, so du is going to substitute 2 dx. Well, there's a dx here, but not a 2. So what do? Well, you can divide both sides by 2 and get dx equals du over 2. So I'm going to substitute u in for the 2x minus 1. So right there. And du over 2 is going to substitute the dx, because that's, so when I got my differentials here, the differential du is equal to twice the differential dx. So I just want to substitute dx. So if I divide off the 2, remember you can multiply or divide by constants, I can get that dx equals du over 2. So I substitute the u for the 2x minus 1 and the du over 2 for the dx. Everything is substituted now. When you do these, you have to substitute all the variables and the differentials. Okay, so if I just rewrite that, it would be 1/2 u to the 1/2 du. Then apply the power rule, so add 1 to the exponent, divide by the new exponent. Simplify it a little bit, and I get 1/3 u to the 3/2. Now, here's the important step. Your original integral was in terms of x. Since it's an indefinite integral, I need to rewrite my answer in terms of x. So just substitute back what x is in terms, or what u is in terms of x. So it'd be 1/3 quantity 2x minus 1 to the 3/2 power plus c. Pretty cool, huh? All right, here's another one. If I find the integral of x times the square root of 2x minus 1 dx. This one's a little bit more complicated because it's similar to the previous example in that the u is the 2x minus 1. Okay, usually when you pick your u, it's the inside of something. And then dx would equal du over 2. But there's an extra factor of x. So I have to substitute that x. I can't just write the integral of x square root u du over 2. I mean, I wrote it down. It's possible to write it down, but you can't evaluate it now because you have u and x. Okay? But this relationship right here establishes, or that equation establishes the relationship between u and x. So what you could do is, if I want to substitute just what x is, solve this equation to get x by itself. So if I solve this for x, you subtract 1, divide by 2. So x is equal to u plus 1, or not subtract 1, add 1 to both sides, divide by 2. So you'd have x is equal to u plus 1 over 2. So your integral becomes the u plus 1 over 2 substitutes the x. The 2x minus 1 is substituted by the u, and you could write that as a 1/2 power. And the dx is substituted by du over 2. Now, I know this looks more complicated than the original problem, but when I go the next step and simplify it, so this is multiplied by 1/2 here, multiplied by 1/2 here, so it's really multiplied by 1/4, and I can factor that out. So I would actually have u plus 1 over times u to the 1/2 power times 1/4 is what this would simplify to. Well, I can factor the 1/4 out and distribute the u to the 1/2. Now I've gotten rid of the product, and I've gotten rid of kind of the composition. It's just u to the 3/2 plus u to the 1/2. Now I can just do the regular power rule. So it's going to be 1/4 times u to the 5 halves divided by 5 halves plus u to the 3 halves divided by 3 halves. Simplifying that and back substituting the u. So how do I get this? Well, if I divide by 5 halves, multiply by 2/5, and then multiply by the 1/4, and that would reduce to 1/10 here. And if you simplify this fraction and multiply by 1/4, you get 1/6. And then substitute the u equals 2x plus 1, put the 2x plus 1 back in, or 2x minus 1 rather, back in for the u in each factor. And that, and this is actually the answer to the problem, okay? All right, let's do another one. So to complete the change of variables in example 4, you solve for x in terms of u. Sometimes it's very difficult. Fortunately, it's not always necessary, as in this example. So find the integral of x times the square root of x squared minus 1. Now this one is very similar, but it's a little different. It's not 2x minus 1, it's x squared minus 1. So you can let u equal x squared minus 1, then du equals 2x dx. Now I have my x and dx here, but I don't have a factor of 2, so I can divide that off and let du equal x dx. So the u is going to substitute the x squared minus 1, and the du over 2 is going to substitute the factors of x and dx. Now sometimes people get confused because the x is over here and the dx is over here, and I'm saying the du over 2 can substitute both of them. The reason you're allowed to do that is because since this is really all multiplication, it's x times the square root problem times the dx, you can rearrange that. Just like 2 times 3 times 4, I can write as 3 times 2 times 4. And in each case, I get 24, like 2 times 3 is 6, times 4 is 24, 3 times 2 is 6, times 4 is... I can multiply in any order. Okay, so I'm just like assuming that property in my head here. And du over 2 is x dx. So the integral becomes integral 1/2 du over 2. So you can factor out the half, add 1 to the exponent, divide by the new exponent, multiply by the 1/2 that you factored out. Simplify those, and you would get 1/3 u to the 3 halves, and then back substitute the x squared minus 1, and you'd have 1/3 quantity x squared minus 1 to the 3 halves power plus c. And you can always check an antiderivative by differentiation. So if I take the derivative using the chain rule, the 3 halves comes down, multiplies, or the 3 halves comes down, multiplies to 1/3. Subtract 1 from the exponent, it becomes 1/2. Multiply by the derivative of the inside from the chain rule, and it simplifies to the 2 here, and the half from reducing the 1/3 and the 3 halves are going to cross cancel. The 1/2 exponent here can become square root, and you can just multiply the x in front instead of the backside. Because differentiation produces the original integrand, you know you have obtained the correct antiderivative. All right, so let's just summarize the steps before we end this video. The steps used for integration by substitution are here. Choose a substitution. Usually it's best to choose the inner part of a composite function, such as the quantity raised to a power or the quantity inside the square root. Figure out your du. Rewrite the integral in terms of the variable u, and find the resulting integral in terms of u. So in step 2 and 3, sometimes you have to solve for x in terms of u to further substitute, like we did, I believe it was example 4. So find the resulting integral in terms of u, then replace u by g of x, in other words, back substitute to get it in terms of x, and then you can always check your answer by differentiating. All right, see you in the next video.